Welcome back to the Foundry by Forge College. I am incredibly pumped for today's explainer. We are diving into threat modeling for wallets. Now, if you remember our last lesson in this applied Solidity development track, specifically in the Designing Smart Wallet Patterns module, we spent a ton of time on troubleshooting network configuration issues. We were literally just fixing the network plumbing, making sure the data pipes were actually connected. But today we are securing the vault. This is where we learn how to systematically anticipate attacks before they ever happen. Okay, let's just do a quick flyby of the agenda for this explainer. 1. Anatomy of a smart wallet. 2. The 5-step workflow. 3. Scoring risks. And 4. Automating the checklist. Think of this as your definitive engineering cure for that baseline Web3 developer paranoia we all get.
All right, Section 1, Anatomy of a Smart Wallet, or Deconstructing the Engine.
So a lot of folks treat wallet security like slapping a massive heavy-duty padlock on the front door, right? But then they completely forget and leave all the first-floor windows wide open. Threat modeling fixes that. It's simply decomposing how your features, your interfaces, and your runtime behaviors actually create opportunities for attackers. We're proactively writing the instruction manual for how someone might break our app so we can defend the windows, not just the front door. Notice how a wallet is separated into these distinct boundaries. You've got the UI, local key storage, smart contracts, and third-party integrations. Each boundary is its own beast with completely unique vulnerabilities. I mean, a phishing prompt in the UI, totally different from a re-entrancy bug in your smart contract. You cannot fix a sneaky UI trick with formal contract verification, and you absolutely cannot fix a smart contract logic bug by just slapping a confirmation screen on the front end. For every single one of those components we just mentioned, we need a core inventory. You literally have to write down 3 things. First, your assets. What are you actually trying to protect? The private key, the user's transaction intent? Second, entry points. How are the bad guys getting in? And third, trust assumptions. What or who are you blindly trusting? Honestly, this last one is huge. In Web3, blindly trusting a third-party oracle, or heck, even the user's local browser environment, is exactly how catastrophic million-dollar breaches happen. To tie all these pieces together, let's look at the concept of a secure withdrawal. This is an atomic sequence that safely crosses the UI, the signing environment, and on-chain boundaries. It is the absolute ultimate test of your architecture. Why? Because it forces an attacker to cross multiple, hardened boundaries all at once. If your withdrawal process is locked down, it means you've successfully juggled threats across the interface, the crypto layer, and the smart contract simultaneously. It's the gold standard. Moving right along, Section 2, the 5-step workflow. Let's open up the diagnostic manual. So here's the sequence: scope, inventory, enumeration, scoring, and decision. This specific flow is brilliant because it takes that messy, chaotic pile of developer what-ifs keeping you up at night and transforms it into a clean, actionable priority list. When you're staring down a massive smart wallet codebase, you can't just guess where the holes are. You just run the manual, step by step. Steps 1 and 2 are all about defining your scope and taking that inventory. Setting your boundaries here is absolutely critical. Think about it. A custodial wallet server-side threats look radically different from a non-custodial browser extension or an on-chain smart contract wallet. If you don't explicitly state what kind of wallet you're modeling right out of the gate, your threat model is just going to be a confused mess. So set the boundary, then list every asset, actor, and trust zone inside it. Then we hit step 3, enumeration. Now, the crucial point here is that you need extreme specificity. You can't just jot down, hackers might steal funds. I mean, yeah, obviously, but that doesn't help anyone actually fix anything. You need to use this exact formula. Actor X exploits entry point Y to achieve impact Z. For example, a malicious DApp injects a deceptive confirmation screen to trick the user into approving unlimited token allowances. Boom. Right? That is specific, it's testable, and it tells your engineering team exactly what attack path they need to block. Okay, Section 3, scoring and prioritizing risks, or what I like to call the math of mitigation. Because reality check, not all threats are created equal, and sadly, we don't have infinite engineering time. The scoring mechanism here is delightfully simple. You assign a likelihood score from 1 to 5, and you literally just multiply it by an impact score from 1 to 5 to get your overall severity score. So if a phishing attack is highly likely, let's say a 4, and the impact is total loss of funds, a 5, your severity score is a solid 20. It takes the emotion and the subjective panic completely out of the equation. But wait,
What happens when you have two totally different threats that both score a 20? Well, that is where detectability comes in. This is your ultimate tiebreaker, also scored 1 to 5. If one threat is completely invisible until it's way too late, and the other one trips massive network alarms the second someone tries it, well, you prioritize the invisible threat for your immediate engineering resources. It's just a fantastic, logical way to allocate your defensive budget. Once you have your scores, they neatly drop into these mitigation buckets. Anything scoring 16 or above, immediate. That goes into your active sprint right now. 10 to 15 is near term. 5 to 9 hits the backlog, and anything under 5, you just monitor. Honestly, this simple math is your absolute best friend when you have to look a product manager in the eye and explain why their shiny new feature has to wait. The math just dictates the priority. Simple as that. Now, for those immediate threats, the 16s and up, you've got to choose your mitigation type. Will it be preventative, meaning you completely rip out the vulnerability? Will it be detective, meaning you build a tripwire to spot the attack early? Or will it be compensating, where you accept the attack might happen, but you limit the blast radius, like putting in a daily withdrawal limit? You have to explicitly decide, are we stopping it outright, sounding an alarm, or just minimizing the damage? All right, Section 4, automating the threat checklist. Because, let's be real, doing this manually in a spreadsheet for every single minor wallet update gets tedious incredibly fast. We need repeatable tooling. The good news is you do not need heavy, bloated enterprise software to do this. A tiny, minimalistic Python script can just ingest a JSON file of your wallet's profile, run that exact likelihood times impact math we just talked about, and instantly spit out a rigorously sorted threat list. It's computationally repeatable and, best of all, incredibly auditable. But I gotta give you a massive pro tip here. And frankly, this is a bit of a warning from developers who have lived through the pain. Automation is awesome, but always, always include a one-line justification string for your scores right there in your JSON file. Like, why is it a 4 for impact? Write it down. Having that single sentence is a lifesaver. It prevents those endless, exhausting philosophical debates with stakeholders 3 months later when they suddenly question why something was delayed. That justification string, that is your absolute shield. Okay, Section 5, conclusion and next steps. Let's do a final review. To recap our core philosophy today, first, always model your threats at the boundaries, the UI, the local storage, the smart contract, because attacks almost always happen right where those boundaries meet. Second, stick to the simple likelihood multiplied by impact math to keep things objective. And third, treat high-value actions like those secure withdrawals as layered problems that need defenses at every single step. And by the way, if you really internalize this mindset, you'll be way ahead of the curve. These concepts are foundational to all the security courses and programs we run here at Forge College. So, here is your mission for the next module. I want you to take a wallet design you already know well, draft a one-page threat map, give me 6 to 10 specific threats using that Actor X exploits Y naming formula, run the scoring math, and bring your top 2 immediate risks to the table. Because next time, we are going to translate those immediate items into concrete technical mitigations. Before we go, I want to leave you with one final thought to chew on as you start mapping out your threats. Look at the code you've written recently, or even the wallets you use every day. Ask yourself honestly, is your secure withdrawal sequence truly unbreakable, or is it really just untested? It's a slightly unnerving thought, isn't it? But honestly, that is exactly the baseline paranoia you need to build unbreakable smart contracts. And that wraps up our explainer for today. I really hope you found this breakdown illuminating and that you feel empowered to start threat modeling your own projects. I highly encourage you to visit forge.college to access more resources, dive deeper into this subject, and explore a wealth of other Web3 related topics to continue your learning journey. Keep building securely, and I'll catch you in the next one.